This was a table that describes how you actually wind up assessing whether or not you have collinearity if you're doing any kind of regression analysis, whether it's logistic regression or linear regression or any one of a number of different kinds of regression analysis procedures. And again, if you remember, what is collinearity all about? Just want to review what that's all about. What's collinearity all about? It has to do with the fact that you're fitting a model, a regression model, and you're worried about that the predictors in the model, the x's in the model, not the y, not the outcome variable, but that the x's in the model, some of them may be very strongly associated or predictive of some of the other x's. That's what you're worried about. And if that happens, and you have what's called perfect collinearity, where some of the variables, some of the predictors perfectly predict some other predictors, then the model won't even run. But even if you have a situation where you have some predictors that are not quite perfectly predicting something, but they're associated with other predictors in some kind of a reasonably strong way, strong association, then what's the problem? What are you worried about? I mean, what's the worry about collinearity? Other than if the model runs, what are you still worrying about? What you're worried about is the fact that the coefficients that you're getting and your ability to judge that model as being a reliable model is questioned. You're worried that if you've got collinearity, then you can't rely on some or many of the coefficients that you're estimating in the model. You can't necessarily rely on any tests you're doing. And in particular, the coefficients, probably some of the coefficients have a very high, abnormally high variance. So, and they're very unreliable, so you can't put any stock in them. And so that's why people are worried about evaluating collinearity, to see if you've got this kind of a problem, to diagnose this kind of problem, and to do something about it. And so there are a number of different ways of dealing with it, and I talked about a way that was sort of more somehow it was more understandable than what I'm showing you in this table. It was using something called VIFs, and VIF stands for variance inflation fractions. And it has to do with what happens if you take every predictor in the model and you fit each predictor on all the other predictors in the model, and you come up with, it's 1 over 1 minus r squared. So it's using the r squared that you would get if you're predicting one variable from all the other variables that are in your model, all the other x variables. And if you got a VIF that was very high, that would mean that 1 over 1 minus r squared is very high, so r squared is probably close to 1, and that would suggest that you have a problem with variables being strongly related to one another, which means that you're getting an unreliable, very unreliable model because the variance is blowing up. And that was a very, it was a nice way to think about how to look at collinearity, but the problem with using VIFs was that it doesn't let you determine how many collinearity problems you have or which variables are involved with which problems, whereas this approach that I'm showing you on the screen here allows you to get at that. This is an approach that uses something called condition indices and VDPs, which stands for variance decomposition proportions. So that's where we were last time. Okay, and what I basically said was, if you look at this table and you try to sort of figure out what's going on here, the first thing you might see is that the table is relating a model. It's dealing with a model which is it's some kind of a regression model, and the variables in the model are an exposure variable, 3 control variables, and 3 product terms involving each the exposure variable with each of the control variables. Those are the variables those are the variables in the model, and there's an intercept. So these betas are the regression coefficients in the model. And the information here is the information you get out of using either a program that proc-reg has if you're doing linear regression, or a program that we now have available. We've had it available for a while. That's called a macro that allows you to consider other models other than linear regression. So regardless of which program you're using, in particular if you use the the linear, you use proc-reg and you use what's called the colon option, you're going to get output that looks like this. And I went over this, and basically what I said is, in the left-hand column is this information. Now, I didn't tell you where this derived, where the theoretical basis for it. That's actually described in the last few slides in this PowerPoint presentation. But I'm not really going to go over it. If you're interested in it, you should look at it. And if you want to talk to me about it, or Dr. R, or any of the TAs about it, that's fine. But the most important thing is, what do you do? What do you mean by collinearity? How do you detect it? And what do you do about it if you find it? Okay. So when you have this kind of an output, and the CI, again, stands for condition index, what you're going to get is a bunch of numbers. The smallest one is going to be 1, and they're going to increase from 1 on up. And what you're looking for is a condition, any one or more condition indices that are, in some sense, high. And high came about, the highness of it, or the decision about what's high, came about from a bunch of work that a bunch of people did, wrote a textbook, and that's the general guidelines that people use nowadays when you're dealing with linear regression. But there's a little bit more of a question when you're dealing with logistic or even other kinds of regression. How high is the issue. And the rough rule was that if you got a condition index that was at least 30 or around 30, that suggested that you had a collinearity problem. Suggested that you might have one. It didn't demonstrate that you had one, because you have to check something else out in addition to the high condition index. You have to check something out about the VDPs in addition to the high condition index. But anyhow, when you go down this list, there are 2 of these CIs that are in bold because they are at least 30. You know, one of them's 30.8 and the other's very high, 99.8, and that would suggest maybe there are 2 collinearity problems. But when I described this at the end of the class, how to deal with this, what I think I said, and I'm going to make sure I repeat it or emphasize it, is that when you try to assess the collinearity the information that you have, you're going to deal with one collinearity problem at a time and try to find whether or not you have a particular collinearity, the one that's the biggest collinearity problem. You're going to try to do something about it. And once you do something about it, you're then going to say, you're going to ask the question, do I have another problem? So rather than actually look at all the high, in this case there were 2 high numbers, you're going to focus on the highest one and say, well, is there a collinearity problem involving this highest one? What's the source of the problem? What can I do about it? And if I do something about it, then I'll ask the question, is there another one? Whether or not there is another one may not be, once I've dealt with the first one. So the 99.8 is, by all ways to consider this thing, is a very high condition index. And what you next do is you look at the row of in this case, the row that corresponds to that, in this particular way of this particular layout. And this row lists what are called the VDPs, or the variance decomposition proportions. And what you do is you look for the highest VDPs in this list, and particularly the question of how high and high. The rough rule was, if you got a VDP that's around 5, it was a rough rule, or higher, then you worry about that may be identifying what the source of the collinearity problem is. Now you notice in this row, the last row, I've got 3 VDPs circled. Now, by the way, I mentioned that the reason why they're called VDPs is if you look at any one column, you notice that the numbers in any one column add up to 1, right? This column adds up the numbers in this column. The next column, they all add up to 1. And what you're basically doing, or what this column is doing, is it's taking the variable that this column refers to and sort of partitioning out the variability of that variable in some way according to the proportion that's explained by these different condition indices, whatever that means. Okay, but that's what it's sort of partitioning out 1, the total variability of beta 1, spreading out over these 8 condition indices. And if there are 8 variables or 8 parameters, you'll get 8 condition indices. That's the way this thing works. So in any case, when you look at this, look at this, the way you should be thinking about this, you should say, okay, this suggests that there are three variables that have something to do with this collinearity problem. And the three variables, you go up to the top, are E, C3, and EC3, because they're the ones that are at the top. And if you were looking at the mirror image, instead of going, you would be starting, instead of going in the row, you'd be starting with the highest condition index that represents a column, and then you'd be going down the column to look at the highest VDPs and the corresponding variables that correspond to that. Now, again, I mentioned that the reason why I'm showing you mirror image is that if you're using the colin option in proc reg, this is the way the data looks like. This is the way the output looks like. If you're using the macro, which I'm going to talk about before we quit today, when you're using the macro, it looks this way. The proc colin option does it, the colin option does it this way, and the macro sets it up this way. But in any case, what do you do here? Now I want to keep talking about this. What you then do is you say, okay, because this condition index is high, and because I have these three high VDPs, I'm going to say I'm going to conclude that it looks like there's a collinearity problem involving these three variables, EC3 and EC3. And what that means is that because of these three variables, yes, there are other variables in the model, but these three variables, by putting them in the model together with the other variables, is giving me an unstable model. And I can't continue with this modeling and with this model by keeping these three variables in there, because it's giving me an unstable model. So I have to do something about it. Okay? And I mentioned that last time. What do you do about it if the three variables causing the problem are E, C3, and EC3? Well, what you'd probably do is you'd say, well, maybe I'll drop one of them. I mean, that's one way to do it. I'll drop one of them, and I won't use that in the model, and maybe that'll solve the collinearity problem, and I won't have any anymore. But which one can you drop? E, C3, or EC3? Can you drop any one of them? You can't, because if you drop E and keep C3 and EC3, the remaining model's not hierarchically well formulated. So the only one you can drop is EC3. So that's what you would do at the first step, given this information. You would drop EC3. Now, by saying that, what do I mean? What would you do next? What would you do next if you dropped EC3? Well, that's no longer in the model, but you have all the other variables that are still remaining in the model. You have E, C1, C2, C3, EC1, and EC2. You got you got these 6 variables in the intercept that's left in the model, 7 parameters that you're fitting in the model. So you'd run that model. And then what would you look for? You'd look at a similar table for that model that has dropped EC3. And how would you work with that table? What you do is, for the table for the reduced model, you'd go down this column, the condition index column, and you look and see if you have one or more, or at least one high condition index. And again, high means at least 30. Okay? And if you find a high condition index, then what you do is on the reduced model, then you look at the row corresponding to that high condition index, and you see if you can find high VDPs. And if you can find 2 or more high VDPs, that suggests where the collinearity problem is, and then you try to do something about that. So you do this sequentially. You deal with the first problem, you reduce the model after you deal with the first problem. You see if you have a second problem, and if you decide there's a second problem, you reduce the model again, or you change the model again, and you keep doing this until you find no collinearity problems. That's the idea. Okay? Now, let me just say, again, we'll repeat sort of what I said. It may turn out that when you decide that there is a problem because of the 99.8 and you decide to get rid of EC3, and then you run the model without EC3, and you look at what the table looks like, it may turn out that the highest condition index is not 30.8 anymore. Because you've dropped the variable, that may have taken care of your collinearity problem. And it may turn out that when you've gotten rid of the worst problem, the EC3 variable, it may turn out that's taking care of the problem, and the highest condition index is much lower than 30. Could be much lower than 30, so you don't have a collinearity problem after that. You won't know that until you run the reduced model. Now, in the reduced model, you may find that you still have a problem. Then you'll deal with that, and then you'll keep doing it until you find no collinearity problems. So that's how you do that. That's how you do it. Now, what I've now said about how you do it is you do it sequentially, and ideally what you're going to do, especially if you've got a model like this where it involves variables, main effect variables like E and C's, and then you got product terms, that if you're going to drop anything, it's going to be a product term. Okay? But that's not the only thing that can happen. I mean, what if, for example, and I have some other examples here, what if it turned out the model didn't have any product terms? The model didn't have any product terms. And one of the variables in the model was weight, and another variable was height. And you looked at the collinearity diagnostics and you found that, hey, there's a big collinearity problem here, and the problem is because of weight and height being highly collinear, causing a problem. What would you do in that case? What would you do in that case? Would you drop weight, or would you drop height, or what's another alternative that you can do to correct the problem? I mean, what it says is that if I have them both in the model, separately in the model is unreliable. That's what if I found I got a high condition index when they were both in the model. Any ideas? BMI. What's BMI? It's a way to combine those two variables into a single variable. And if you put that single variable in there, then you've probably taken away the collinearity problem, because now you've got one variable that's describing what's going on in the two variables, and you may find when you fit that model, there's no collinearity. So that's another way you can deal with collinearity. Define a new variable. Rather than drop a variable, define a new variable that makes sense. And of course, the variable has to make sense, because if one of the variables was age and the other variable was sex, and you decided they were very highly collinear, how are you going to combine them in a variable that makes sense? I'm not sure what you do. It's not clear how you would do that. So you can't just automatically combine variables into a new variable unless it makes sense. So weight over height squared makes sense as a BMI. It's weight over height squared. It's not height over weight squared. It's weight over height squared. So that's how you do that in that case. So I'll say a few more things about that. But now I want to show you another thing. Okay, I showed you this. Now I want you to look at this table. I mean, there's some writing at the bottom, but let's just look at what's on the top of the table, the numbers in the table. Okay. Now you notice from this table, this again is got the condition indices and it's got the VDPs, and it doesn't have any product terms in the model. So it's E, C1, C2, C3. And you notice that the highest condition index is high, right? 78.8. That's a lot higher than 30. So that would suggest that there's a collinearity problem, right? I mean, in terms of what we were doing. But now you look at the VDPs, and there's only two of them that are high, even reasonably high. And I put them in bold, the 0.725 and the 0.700, right? That can happen. You can get this. Okay, now, these are just some things I made up, but you can get this type of thing. So if you got this, what's the collinearity problem? Now I wrote something about this, but what it looks like, what would you do? You would go up to the top and you'd say C3, that's this one, and this one is the intercept. What on earth does that mean? There's a collinearity problem involving this variable C3, whatever it is, age, race, sex, or whatever the variable is, and the intercept. What could that mean? What could that possibly mean? Well, it actually might mean something, but it might not when you actually look at your data. Because you've got this variable, if C3 was highly collinear with the intercept, what's the characteristic of the intercept? What variable does the intercept what's the variable that corresponds to the intercept? What's the variable? It's a variable that doesn't vary. What's the variable? What value does the variable take? 1. It's the variable 1 for everybody. That's what the variable is for the intercept. Okay? So if C3 is highly collinear with the intercept, what would that mean? What's another way of saying what that would mean? It would mean that C3 doesn't change, hardly changes at all, right? Because the 1, that doesn't change. So if there was a highly collinear, if this variable was highly collinear with the intercept, that would mean, the variable's not changing. How could you determine whether that's true or not? You look at your data. If you look at your data and it looks like the variable is changing, as far as you're concerned, changing enough, you basically say, even though this was high, the fact that I only found this high VDP and this high VDP tells me that I don't have a collinearity problem. Even though I had a high condition index and I found 2 high VDPs, but one of them was on the intercept. And unless the variable that I'm worried about is not changing at all, then I don't have a collinearity problem. So you don't automatically have a collinearity problem if the highest condition index is high. It may not be. Okay, so that's one message. Another message is, look at this table. What's the difference about this table? There's all sorts of, see, these people that wrote this book, I don't know how many years they spent on it, but they spent a long time trying to consider different situations, and they considered this situation. What's different about this one? What's in the table? Well, I got the same starting model here that I'm dealing with, but look at the condition indices. Okay, both of them are very high, and they're almost the same, right? This is sometimes what they called a competing dependency. That was just a term that they used. Okay, but they said, well, this situation is not really the same as this situation, because this one of them was high and the other one was a lot smaller than it. Okay, they said, well, when you have this situation, maybe you have to think about the collinearity problem a little differently. And what they suggested, this is why this thing is not completely carved in stone. It's not the first problem with it is how high is high. That's the biggest problem with it. But then what do you do if you got something like this? What they suggested was, and this is what most people would do if they wanted to assess this, what they suggested was that if you've got 2 high condition indices that are almost identical, then you might argue that there is a collinearity problem involving what's in both of these rows together. Both of these rows together are causing the collinearity problem. So if you looked at this information that I have in both these rows, and you were going to try to say, okay, what's the problem? I'm looking at both these rows. How would you conclude this? How might you proceed with this? Just trying to give you an idea. There's loosey-goosey stuff here, I'm trying to tell you, but how would you proceed with this? Well, what you do is you'd say, well, it looks like, there was a problem with EC3 and EC3, and maybe there's also a problem with EC2 and EC2. That's what these two say. Isn't that right? Isn't that what these 2 rows say? So it looks like, so if you were looking at both of them together, what would you tend to do? What would you be thinking about doing? Well, if the problem involved EC3, EC3, C2, and EC2, and you wanted to do something about the collinearity problem, what you'd probably do is say, well, look, I'm still going to drop something. Okay, which one would I drop? Well, maybe I drop EC3 because that's related to the highest one. Maybe I drop that and I reduce the model and see if that takes care of the problem. And if it doesn't, I drop another one. Or I drop EC2 and see if that takes care of the problem. Or I may have to, once I drop it, I go refit the model and see, for the reduced model, and see if I still have a problem. So that's sort of what this competing dependency approach is, it says. So that's another thing. So I'm just telling you that there's this issue that we are all worried about when we do an analysis, that we may have an unreliable model, and collinearity is a way for diagnosing that and doing something about it. Now, another thing to say about doing something about it, suppose I go back to this thing, go back to the original thing, the original layout, the original output that I showed you, and suppose I dropped EC3. I decided to drop it because that made sense in this case. what does that mean about EC3? What can I conclude about EC3 because I've dropped it because of collinearity? What can I conclude about whether it's a significant predictor or not? That's what I'm asking. If I drop EC3 because of collinearity, because of what this table says, does that mean it's not a significant product term? It's not a significant predictor? It doesn't mean that. It doesn't mean that at all. What it means is that I don't have enough information to assess whether that variable is a significantly predictor given all the other variables in the model. So once you drop something because of collinearity, it doesn't mean that variable clearly is not important. You just can't assess it. That's the problem. That's what you're doing when you drop a variable because of collinearity. You just can't fit that model, and that variable doesn't allow you to do that. Okay, so that's another thing, another important thing to consider. Okay, now I'm going on a little bit, and I'm skipping a few things here, but I want to talk about, okay, what do you do about collinearity? A list of things. What do you do? Okay, what are your options? Well, number one on this list is what I did. What is what I described with that original data set. I dropped one of the variables. Drop one or more variables involved in a collinearity problem. Recommend doing this sequentially by refitting a new model and assessing collinearity each time a variable is dropped. That's usually the first thing you consider, okay, if you can do that. Another alternative is to define a new predictor, like that weight-height example. Define a new predictor, but it's not appropriate if the variables you're putting together don't have any meaning when you combine it. Okay, so that's a second thing. Okay, now there's a third thing called centering, so I'm going to talk about very briefly, and I'm going to go back to this in a second, because the fourth thing says, well, if the model's unreliable, unreliable given the data that you have, another thing you could do is add more data, and maybe you'll get a model that is reliable. I mean, a model that you decide is unreliable because you can't determine something about a certain variable because of the data that you have. If you took 100 more people in the data set, if you got a larger data set, maybe you wouldn't have that problem. Okay, so that's a fourth way to deal with collinearity. Well, there's a big problem with that. What's the biggest problem with that? Biggest problem with that is you're doing a study, you spent a lot of money getting your data, you've got your data, you just can't collect another 100 people that easily, okay? Maybe you can. If it's an experimental study, maybe you can add more experiments or more people to the study. If you think you can, but maybe you can't because of how much it costs. But so that's the fourth thing, add more data, and maybe that'll solve the problem. So what do we mean by centering? Okay, that's the third thing, which is another option, but you may notice that when I wrote this down, I said it's a debatable procedure. Because a lot of people try and it usually doesn't work or it doesn't solve the problem. So one way to talk about, or what's usually done when you're talking about centering, you've got this variable x. X might be age. And age is involved, and you decide age is involved in some collinearity problem. So what you might do is you might change that variable in your data set from just age. In other words, rather than having the age on each individual in your data set, you take the mean age of everybody in your data set. If you have 100 people, the mean age of the 100 people, and then you take each person's age and you subtract from it the mean age for everybody else. That's x minus x bar. xi minus xi bar. Xi is the ith variable, the ith x, and then you subtract from it the overall mean for everything. Now somehow, when you do that, that often solves the problem it often seems to solve the problem that you may reduce the condition indices so it looks like you don't have collinearity. It turns out that often doesn't really solve the problem. It often just may give you, looks like you've dealt with a problem, but you haven't really done it. You still have collinearity. You've just centered the data. So there's discussion about that, and there's an article in a journal called the American Statistician. You've heard of that, the American Statistician? American Statistician is sort of like the Time magazine for statistics. I used to call it the Newsweek of statistics, but Newsweek's no longer around. So that's where, people write articles about more general things that most people who know a little something about statistics but not a lot can read. But anyhow, this article said, well, maybe this is not a good idea. So centering is something that, in fact, let me just show you when you might want to do it and what are some of your options. But it's still not a good idea, so I'm not going to spend a lot of time on it. But suppose you're fitting this model. What is this model? This is let's say, and it's a linear model, right? I didn't say logit anything. So I've got y equal to beta naught, beta 1x plus beta 2 x squared plus a. What might you worry about this model, about collinearity? Well, you got the same variable in there twice, but it's not there exactly the same. You've got the variable and the square of it. So the square of it isn't the same variable. It might be highly related to that variable because it comes from that variable, okay? So you might say maybe if you ran this model, you might get some condition indices that are very high, but there's an alternative way to deal with this. One way is to replace x with x minus x bar and x squared with x minus x bar square, and then run that model and see if you have a collinearity problem, okay? Often when you do that, you might find the collinearity disappears, or at least the condition index gets smaller. That doesn't necessarily mean you don't have a collinearity problem. That's what this article said. So approach 1 is often considered reasonable, but approach 2 is not considered appropriate. Approach 2 says replace x with x minus x bar and then replace x squared with x squared minus the mean of the x squared values. That doesn't work. That second one, that definitely never corrects a collinearity problem. First one might help, but it's very debatable, and I just generally, you might try it, but generally it's not going to work. So, and if you have your data and you want to try it, and it's important to you, you ought to read that paper that I referenced. Now, here's sort of the last issue that is important to talk about the collinearity, and it has to do with this. What I've described to you was, and what I've shown you was the collinearity diagnostics that you use when you're dealing with linear regression. They also relate to logistic regression, but there's a problem. And the problem is stated on the slide in a lot of words here. And what I said here is collinearity diagnostics are derived to identify when the variances of the estimated regression coefficients become extraordinary or extremely large. In other words, what you're worried about is you've got a model, you've got betas in the model, whether it's a linear model or a logistic model or some other model, and what you're worried about is when you estimate the betas in the model and you get the standard errors of those betas, they're really high, or some of them are really high, okay? Now, it turns out for linear regression, there's a certain formula, mathematical way, that in linear regression you can get what the variances look like, a mathematical formula for what the variances are. Now, for nonlinear models like logistic regression, which is not a linear model, it turns out the formula for getting the variances is a different formula. It's not the same formula. Now, I've just written roughly something, a term that describes what the formula is for linear regression, and a different term what the formula means for logistic regression. And most of you won't care about this, but the message is it's a different formula. In other words, if you wanted to use linear regression, the formula, the way you're going to get how high is, you're going to get the variance and see whether they're high or not, you're going to get the variance from something called the x prime x inverse matrix, whatever that is, okay? If you're going to do it using logistic regression or other kinds of regression that haven't involved maximum likelihood, you're not going to use this matrix, or the computer's not going to use that matrix. It's going to use some other kind of matrix which gives you the variances and the covariances, and it's called the information matrix, I, and the inverse of the information matrix. Now, all I'm telling you is that if you wanted to get collinearity or evaluate collinearity and determine whether you have it or not, and you're doing logistic regression, you can't do it the same way that linear regression does it. You have to use a different formula for whether the variances blow up or not. And it turns out that that colin option in proc reg only works for x prime x inverse. It doesn't work for any other model. And that's why somewhere about 25 or so years ago, some fellow, his name was Matthew Zach at CDC, said, oh, I better use the information matrix to decide whether I have collinearity for logistic regression. So he came up with a different program, which was called a macro, to try to come up with the right way to determine. Now, you're still going to get condition indices, and you're still going to get VDPs, but you're going to base it on the correct variance matrix, or variance covariance matrix. And that's what this says here. So that's why there's a macro. I'm trying to tell you that's why there's a macro. The reason why is if you didn't have it, you'd be using the wrong variances. Okay? So another way of saying that is in classical linear, I'm just writing it easier on a slide here. In classical linear regression, condition indices and VDPs are derived from something called the x prime x inverse matrix, whatever that is. Okay? And I don't want to spend any time showing you that because it'll take me the rest of the year to show you that. I don't know. In logistic regression, Cox proportional hazards regression, which is the topic that we're soon going to see, and other models, which are fit using maximum likelihood techniques, the condition indices are derived from the inverse of what's called the information matrix. So you have to have a program that makes that happen, and that's what the macro does. Okay? So without saying any more than that, I'm going to talk about what the program does, what the macro does. So computer programs for carrying out collinearity diagnostics. Well, Sas, Sas, Stata, and SPSS are the three ones I'm most familiar with. Now, I'm not sure whether R has, what R has about this. R conceivably has something. I don't know how many of you use R. Some of you might. But SAS is what we're primarily using. That's why I'm focusing on this. Now, SAS, as I just said, computes CIs, condition indices, VDPs, and even VIFs using the colin option. But SAS macros are available for logistic regression, Cox regression, other kinds of regressions. And Stata only does it for linear regression. It doesn't have a macro. And SPSS doesn't compute CIs or VDPs. So if you want to use another package, you have to use some other macro, or you have to write the macro to do it. But SAS, there is a macro for doing it. So I now want to talk about how the macro works, okay, and what it does, okay. So the first thing I'm going to show you is how the macro works, okay. Now, a macro is an extra program. It's a special program. You knew that? I'm not sure if you know that. It's something that you can write using the language of the package that you're using to do something extra that's not in the package. And if you write this, it's an extra computer program. If you write that program and you store it somewhere on your computer or somewhere in the computer system, you have to have a way, if you're going to use it, to access this. You have to know where it is. So you have to have a way of telling the computer, if you want to use it, where it is. So on the S drive for our school, the macro that you can use for logistic regression and some of these other things, it's called the colin underscore 2011. That was when the most recent version was done, .sas. It's in this, you have to write this statement as a percent include, and then you have to write the statement to tell the computer if you want to get collinearity diagnostics printed out or for your model, you have to tell the computer that's where it should go to do this. So you have to write this macro file name, and you have to tell the computer where it's located. Then, now notice that what I've done in the next couple of lines here, you see I've said proc logistics, so what does that mean? What am I doing? What am I doing? I'm fitting a logistic regression model using proc logistic, right? And I'm telling all this is telling what the name of the data set is. It's a different data set. It's called VETS. Descending, I have some other bit of information that I want to talk about a little bit. And then I write the model. It's got some different variables, and it's got something slash COVB, whatever that is. And then it says run. And then it's got something at the end of it. It's got percent colon, and then it's got some stuff. Okay. Now, and then it's got run. Now, This statement, the percent include, where you have to tell the computer where it is, some of the information that I've circled in red on the proc logistics statement, and the information that I've circled in red and what's in the box over here, that's what you have to add if you want to run this macro. Okay, so in fact, you may notice from this from what's on this screen here, as you see, it says proc logistic, and then I've got some things over here, and then it says proc pH reg. What's pH reg? Well, we don't know this yet unless you've had it in another course. pH reg is a different package. It's a different program. What does pH reg do? It does survival analysis. It does Cox proportional hazard survival analysis, which we're going to learn about, you know, after the exam and a little bit after Eli, Dr. R talks about some other things that we need to add to the course. But this is the code. Okay. Now, let me just show you what's in the code here. First of all, you see the word info. See the word info, that circle? Say, now you don't need that here. This is what I've written in blue is just telling the program where to find the macro on your computer, and that's where it is in the School of Public Health. Info is something you have a choice of what you write here, but if you write this here, when you put this percent colon statement, the percent colon statement is telling the computer to run the macro on this model that you've talked about. And when you put this thing in here, you have to the info, whatever name I put in over here, info has to go over here. It has to be the same thing. If I write info, if I write Kleinbaum. If I write Kleinbaum over here, it has to be Kleinbaum. Okay? Whatever I put over here, I have to put over here. And then then over here where it says output, actually in the last couple of years it's changed what you have to do. For output, you have to put some other name other than info or whatever you've used here that goes here, you have to choose something else. Doesn't matter what you do. Okay? So you see I wrote out, O-U-T-L-R. Now, I just chose that. What do you think? Why did I write O-U-T-L-R? L-R stands for Logistic Regression. Why do you think I wrote O-U-T-C-R over here? Because I'm not fitting a logistic, I'm fitting something called a Cox regression model. So I wrote something different. But you notice it says file over here and it says file over here. So whatever I write over here has to be the same as what I write over here. Okay? I'm just telling you how it works, okay, how the macro works. What you have to, and that's all. You have to tell it where it's located, and then you have to write the percent colon statement in order to get the macro to work. And once you get the macro to work, you're going to get output. Okay, so let's look at some output. Well, the percent. This is what I've said on the next slide. The include statement tells SAS where to get the macro. There's some other things on that statement. There's a cov out. See, cov out, C-O-V out. Well, you sort of have to put that in there, but it does tell the computer to do something in the data. You don't really need it. You'll never necessarily see it. Creates a data set of the variance covariance matrix, which is going to use to compute the collinearity diagnostics. But the percent colon thing, that's over here, the percent colon that's over here and over here, you need to have that statement because that invokes the macro. That tells the computer to run the macro. Okay? And if you want to see the variance covariance matrix on your output, you see this thing called, where is it? COVB, C-O-V-B. I've got it in both places. That'll give you what the variance covariance matrix, most of you won't care what that looks like. Because if you want to just get the collinearity diagnostics, you don't need that. But that's what you can put in. So let's look at the output. Okay. Now, the first thing I'm going to show you is the output that you would get if I actually didn't, if I used the VETS data set. You notice if you go back to this, it says VETS. So what I'm doing here is I'm running the collinearity diagnostics using logistic regression on this data set with a certain model. I'm also using pH reg on the same data set using the same variables, but I'm using a different program, pH reg. Okay, And I can also, on the same data set, pretend I've got a linear model. And when I do that, this is the output I get down here. Now, you notice it says, the output uses the following model statement in Sas's regression procedure for linear. It says model status equal to, it's got all these same variables, then it's got slash, and you see colon. See that? Colon. That's the colon option. So if you're using linear regression, you would put slash colon, and you'll get output like this. Now look at this output. Look at this output. You notice the output, it's got number 1 through 9. Now how many variables, how many parameters do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So you're going to get 9 condition indices. Now you notice that if I look down on the condition indices column, there's some other terms here that explains where the theory, but I don't care about that right now. I don't really care about explaining that to you. But if you look at the condition indices, you see the one I've circled, 21.37548. What's that telling you? What's that? That's the highest condition index that I got when I fit this model on the VETS data set. Isn't that what it says? That's what it says. Okay. Is that high? No. Not only is it not 99, it's a lot less than 30. So if you see something like that, that first thing that should tell you is you don't have a collinearity problem. Don't worry about it. You don't have a collinearity problem. Don't even bother to look at the VDPs. You notice next to this, you see it says variance, proportion, intercept, treatment. These are all the VDPs. Some of them are high, and some of them aren't that high. Okay? But if the highest condition index isn't high, you don't have a collinearity problem. You just stop there. And that's what this says. Okay? Now, let me show you the next slide. The next slide is what I get when I use the macro, not colon option. When I use the macro, using the code that I showed you previously here, when I use the macro on the same data set with the same variables. Okay? Now, you notice it just fits, it gives me the variables, the parameter estimates, and so using proc logistic. Now notice at the bottom of the slide here, you notice I've circled, you see the 22.7557? Now you notice this is the mirror image. This is the picture of the mirror image because we're using the macro, we're not using the colon option. But that's the highest condition index. Okay? Is it identical to the highest one that you got when I used linear regression? No. Will it be identical? Well, clearly it's not identical. Will it always be close to the same thing? No guarantees that it's close. There's no guarantees. So if you had to choose between using the macro or using the colon option when you've got logistic regression, you should use the macro. I mean, it's possible you might get a similar answer, but it's not guaranteed. So you want to use the macro. And again, what does this say? What does this say about collinearity? No collinearity. So I'm not going to worry about anything else here. Okay, I'm just trying to show you what happens here. Okay, last thing is the next slide. I've used pH reg. Same data. I'm using a different program. I'm using a different model. I run the model and, I'm using the same set of code, but the code I showed you for the VETS data set, but I'm now using pH reg. Look at the highest condition index here. What's going on? Is that weird? You notice the highest condition index for the other two was 22 and 21. This is a 2. Okay? Now, I had a student maybe about 20 years ago who was doing his dissertation on collinearity, and he was trying to figure out one of these problems. One problem was, what's the difference between survival analysis or Cox regression and linear regression or logistic regression when you're trying to assess collinearity? Because what this suggests is, what does this suggest about cut point? You remember what was the cut point we were using for linear regression? 30. And that's roughly, as you can see, maybe relatively okay for logistic regression. But what does this suggest for survival analysis? Should it be 30? Should be lower. But nobody's ever come up with something lower. It's not there. So one of the things one has to worry about is if you're doing survival analysis using Cox regression, you're trying to assess collinearity, it's not clear, and some people have made some proposals about what the lower value should be. One proposal was 20. Another proposal was 10. And they wrote it in papers. Now, nothing is a guaranteed thing. So you have to decide, looking at these papers or making some kind of decision, what you're going to do. You have to make a decision if you're going to assess collinearity for survival analysis. You have to come up with some reasonable cut point that you think. And nobody's ever proved, and this fellow that did his dissertation showed that for different situations, the cut point could be varying all over. The value when you get collinearity could be very low or very high. Never proved anything. Okay. So you can use these macro. There's this macro, it's available. You can use it for logistic. You can use it for survival analysis, pH-reg. You can use it for GenMod, which we talked about, I think it was talked about in the lab, which is also used for correlated data. You could even use it when you've got a data set which was based on a complex survey design. The macro allows you to get collinearity diagnostics for that. Okay, and depending upon what model you're using, whether you're using a logistic model or a linear model or a survival type model, there's the cut points are sort of more debatable if you're using a survival model. But that's where we are with regard to collinearity. Okay, so again, what is collinearity? It's a problem you're worried about getting, because of the predictors in the model, getting unreliable estimates or even a model that doesn't run. There are ways to assess it. The way that's primarily used is this condition index VDP approach. I showed you how to do that. I showed you a little bit about the program, how you run the program. After the exam and all that, you'll get some homework exercises where you'll be asked to run the program so you get some practice with that. And one thing's for sure, on the final exam for the course, you're going to get to answer at least one question where you have to assess collinearity for some data set that you'll be getting at the end, in the take-home part of the final. Okay, so I'm done with this. Any questions? And I know there may not be very many questions because what are you worried about now? I'm worried about the exam. So you were probably hoping, gee, I wish he'd finish. And he finally finished. Okay, but you can ask a question anyhow. Okay. Now, I'm not finished with everything because I want to talk about this one other thing. Okay, and then we're done. And we are going to leave early, but it's not going to necessarily be super early, but I want to talk about the other thing. And this won't take that long, though. Okay, now here it is. Here it is. Logistic modeling, assessing trend with continuous predictors. This is something I just sent you, and it's up on Blackboard. Okay. Now, this is a very simple idea. Okay. Now, let's look at the first slide here. Consider the following model. Okay. What kind of a model is this? Top of the screen. What model is this? It's a logistic model, right? And there's only one variable in the model. What variable is it? Age. And let's suppose age is in the model as a continuous variable. Okay. So let's suppose age is your exposure variable and it's a continuous variable. I mean, we could have other variables. I just want to make it as simple as possible. Okay. So if you think about it, you know, when you fit this model, or when you think about what the true value of beta is, if beta is, let's assume beta is positive. Okay. If beta is positive, and you think about this model, the logit P of X is the log of odds. Okay. If beta is positive, then the log odds of age, when you plug in a different value, increases linearly as age increases. Isn't that what this says? Doesn't this model say that the log odds linearly goes up as age goes up? And here's a picture of it. If you fit this model, that's what you're going to get. Okay? So this model sets things up so that the age relationship to the outcome as far as the log odds concerned is linear. Well, is that going to be true? And how might you evaluate that? That's what I'm trying to say. If you put age in the model as a continuous variable, you're assuming there's this linear relationship that may not hold. Okay. What would you do? We look at the next slide. Okay. Suppose instead we categorize the continuous variable age into 4 categories. age I going from 1 to 3. Well, actually, it should be I from 1 to 4, denoting but I going from 1 to 3, denoting dummy variables in category 4 being the reference group. So suppose we fit this model. Logit P of X equal alpha plus beta 1 age 1 plus beta 2 age 2 plus beta 3 age 3. So putting in 3 dummy variables for 4 categories. Okay. Now, what about this model? What does this do related to linearity? Does this force linearity? You know, this model forced linearity. But what does this model allow? It allows you to get estimates of these betas and estimates of the log odds that jump around, that aren't necessarily linear. Because if you fit this model, you're going to get, well, beta 1 is the log odds for age group 1 compared to age group 4, and beta 2 is the log odds for age group 2 versus age group 4. Beta 3 is the log odds for age group 3 versus age group 4. And because you put them there as categorical variables, you haven't forced these betas to go up linearly. So you haven't set that up. So if you want to evaluate whether they're going up linearly, you could fit this model instead of this model, which forces it, fit this model and see what you get. That's all I'm saying. It's a very simple answer to this. In fact, if you think about it, if you do this, and all I've said is beta I is the log odds for one age group compared to age group 4, you could fit the model, get these beta hats, and plot them. And if they look linear, you might say, okay, if the plot's linear, you can say, well, look, I have now good reason to use age as a continuous variable. That's one way to deal with it. This is a way of just fitting a model that allows it to be not linear, seeing what you get, and then if you get something that looks linear, this sort of looks linear, although it's not that linear. It's a little parabolic, but this is how you might evaluate linearity. That's what I mean by testing for or evaluating trend. Now, I haven't done a statistical test for trend. I've just fit this model with these 4 categories, and I've plotted these things. Now, how might you do a statistical test? So how do you do a statistical test for trend? Okay. Well, here's what you could do. Trend test. See this model? Y equal to, now I've got different names. I don't have them calling it beta. What's this? Tau or tall. Tau, I call it tau. But tau 0 plus tau 1 times age group. That's a model. What kind of a model is this? Linear or logistic model? It's a linear model. And Y is whatever you're getting for the beta hats. So Y is 3 values that you're getting if you're getting 3 beta hats for the three the 3 betas in this model. Okay. And what I'm doing is I'm saying, okay, let's fit this model, and age group takes on the value 1, 2, 3. I mean, for the different age group values, okay? And what I'm basically saying is, isn't this a model that says I'm fitting age group, and I'm using a linear model to predict these outcomes, to predict the different betas. That's all that does. And so if I then evaluate and I test for tau 1 in this model, and I find that it's significant, I have evidence that there's a significant linear trend. So that's how I can test for trend. You got that? That's the idea, how you can test for trend. Okay. Now on the next slide, I give an alternative way to do that, but it's basically the same thing. It's to recognize that actually alpha hat plus beta I hat is really the log odds in age group I without worrying about age group 4. So you might just fit, instead of using Y being beta I hat, you have Y taking on alpha hat plus beta I hat, 3 different numbers where you add alpha hat to it, and you fit this model and you still test for tau 1 equals 0, and if it's significant, then you say, I got significant trend. So that's how you can test for it. That's all I was going to say. If you want to evaluate whether there's significant trend, you can do it simply by fitting this model, plotting it, see whether it looks linear, or even then fitting a linear model and to see if the linear model looks linear and test for it. Okay? That's it. Okay? So that didn't take that long. And it's almost 10 after 5, so isn't it time to quit? It is, because you want to get on to the next thing. You want to go home. You want to prepare. I don't know. The debate's over. I'm sure you had a great time watching the debate last time. I know who you were all rooting for. I won't tell you, you know. And by the way, what happened to me yesterday? I had cataract surgery. So what am I doing here? I'm crazy, okay? So, in fact, what happened was, just to tell you, my right eye here, my right eye, it was on the right eye, okay? And my right eye has better vision today. I have to spend a couple of weeks figuring it out. But what happens, the lens in my glasses now doesn't work. So if I look at you with my right lens, I see a blur because it doesn't work anymore. I look at you with my left eye, you look okay. But in 2 weeks, I'm getting left eye cataract surgery. So after that, I'm going to get a new set of glasses, and then I'll be able to see better overall. And there you go. Okay, good luck on Thursday. Okay? Yeah, and let me get out of this. Okay, let me get out of this. Let me check this. Let me go.